Again, to examine the concept known as conservative force fields to develop the idea of something known as geopotential, which we'll use throughout the rest of this material. Consider a force field. The work done by this force field on an object as it moves from point A to point B, as shown graphically, is equal to the integral from A to B of f dot dl. So this is a line integral, and it's the integral of the force acting along the path from A to B. This is the work done by the force on an object. So by Newton's third law, the work done against the force field to move an object from A to B is minus the integral from A to B of f dot dl, this line integral. Now, the work done against a conservative force field to move an object from an arbitrary point A to another arbitrary point B is independent of the path. That's how you define a conservative force field. The work is path independent. So as shown then, the integral along the path C1 of minus f dot dl is equal to the integral along the path C2 of minus f dot dl. So it doesn't matter how we get from A to B, the integral is the same in this conservative force field. The implication of this is that the work done against a conservative force field on a closed path from an arbitrary point A back to A again is 0. So consider the closed loop shown there with the path from A to B C1 and the path from B back to A is C3. The integral for the work done is minus the path integral from on C1 of f dot dl plus the path integral along C3 of f dot dl. But C3 is just the negative of our C2, and so we can replace the integral plus C3 f dot dl as minus C2 f dot dl, and what's inside the brackets becomes 0. And so the work done along a closed path, which is indicated by the integral with the circle through it of minus f dot dl, is equal to 0. Now, since both the point A that we chose and the loop are arbitrary, we can use Stokes Theorem, and if you need to look that up in a maths textbook and revise that, then fine. Stokes Theorem says that the surface integral of the curl of f dot n, which is the normal to that surface, dA, so it's an area integral, is equal to the closed loop integral of f dot dl. And since we've shown for a conservative force field that closed loop integral is equal to 0, it means that the curl of f is equal to 0. Alternatively then, we can define something known as a scalar field, which is simply a field of scalar values, such that f is minus k grad of phi, where k is a constant and a property of the object under consideration, and phi is a property of the source field. So we can define a couple of conservative force fields. The first one is gravity, which we'll be looking at in this series of lectures. Fg is minus m grad phi of g. So phi subscript g is the gravitational potential or geopotential, and m of course is the mass of an object in that gravitational field. The electric force, Fe, is minus q grad phi v, where phi v is the electric potential and q is the charge.